In this video, I'd like to introduce you to the inverse trig functions. We're going to look at the inverse sine and the inverse cosine, and we're going to see the domains and ranges and some graphs of these functions. And then I'll also show you how to use our traditional table of special values of sine and cosine to actually compute the values of the inverse sine and the inverse cosine, just using the same table in a different way. Okay, so recall that what an inverse function's job is, its role, is to undo the operation of a function. We want to take something that would be an output of a function and transform it back into the input that produces that output. So if I'm going to draw up a plot of the cosine function to start with, I draw cosine. Cosine looks like this. And then we've got some negative side and so forth. Now, this function, the cosine function, is periodic. Once we have the information from 0 to 2 pi, we can repeat that information or repeat that pattern all the way along the x-axis, and we know what the cosine function is going to do. This causes us some difficulties when we're trying to define an inverse function, because the cosine function globally is not one-to-one. You can see that if you plug in different inputs, you'll produce the same output. If I plug in 0 to the cosine function, I get an output of 1. And if I plug in 2 pi to the cosine function, I also get an output of 1. So if I'm trying to define an inverse function, I have to restrict my attention to an interval where cosine doesn't repeat itself. It doesn't reuse any outputs. When we do this traditionally, what we do is to use the biggest interval around 0 that we can to define the inverse trig functions. This is kind of the traditional way to do it. It's possible to invert the cosine function on different intervals, but usually you can use this base inverse cosine function, or this simple definition, and extrapolate from that any extra information that you need, just by thinking about angles and quadrants and so forth. Okay, so well, the first thing we want to do is just restrict our attention to the biggest interval where cosine doesn't reuse any values. So if we look at the graph that we've drawn so far, if we include any negative numbers in our interval, we would reuse these positive numbers. So we're going to exclude those from the domain. Okay? In addition, anytime we go past pi, we'll be reusing these negative numbers, so we want to exclude that. Okay? So the section of the cosine function that we're able to invert has a domain from 0 to pi. The outputs range from 1, for an input argument of 0, to negative 1. Okay? So the cosine function on the interval from 0 to pi has outputs that range from positive 1 to negative 1. If you wanted to write that in domain range notation, you could write it like this. You could say the cosine function, let's think about maybe theta as being our input. We're going to take the interval from 0 to pi, that's our domain, and we're going to map this. Now we have an option. We can think about using the codomain or using the range to denote what's going on. If all I need to do is specify codomain, then I can say that the cosine function maps the interval from 0 to pi into the real numbers. But if I want to be more specific, and that's going to be really helpful here, I'll actually specify the range much more carefully. So the actual outputs of cosine for the domain from 0 to pi, they vary from negative 1 to 1. So I can say that cosine takes the interval from 0 to pi and maps it into the interval from negative 1 to 1. This is actually the range of this function. Okay? And now, the inverse cosine, its job is going to be to reverse this function, to switch the roles of the domain and the range. So here's one notation for the inverse cosine. We could say cosine to the minus 1 of, and I'm going to call its argument maybe x, because it's not going to be the angle in general, it would be the output of cosine, which is usually like a length or something. So say you have cosine inverse of x, that is going to be a map that takes -1 to 1. That'll be the domain of the inverse cosine, and it will map that from 0 to pi. So the domain of the inverse cosine is -1 to 1. Those are the possible outputs of the cosine function. And then because of the way that we're defining it, this inverse cosine is going to take on a value between 0 and pi. So between 0 degrees and 180 degrees. Okay? If we want to look at what this function looks like, we can use the graphical connection between a function and its inverse, that of switching the inputs and the outputs. So when I draw the original function, the inputs are on the horizontal axis and the outputs are on the vertical axis. But when we draw the inverse function, we switch those axes. So this vertical axis gets kind of flipped over onto the horizontal axis, and the curve responds by flipping over in the corresponding way. So let's draw out a graph of the cosine inverse. Our domain is from -1 to 1 for the cosine inverse. Let's call that -1, and let's call that 1. Okay, and then the range should be from 0 to pi. So we expect all of the outputs of the inverse cosine to be in this region. If we pin some things down, we can see that the cosine of 0 as an input gives us 1 as an output. So switching those to see what the inverse function does, we can see that at an input of 1 here, we should see the output of 0 for the inverse function. Okay, so we're taking this whole curve and we're flipping it over. If we do that, then the curve looks something like this. Okay. Not the best picture in the world, but not too bad either. At the value -1, or the output of -1, the input was pi. So the height of this curve should be at pi. We see that the function cosine has an output of 0 when the input is pi over 2. So the value here should be a height of pi over 2. So we've taken this whole curve and we've flipped it over. We've flipped it over the line y equals x, and that gives us the graph of the inverse cosine function. Okay? So that's the domain and range of the inverse cosine function. That's a graph of roughly what it looks like. And now, if you want to find the values of the inverse cosine function, you can use this table, but in the reverse of the way that we normally use it. So, if I'm trying to compute a value of cosine, I think about finding the input on the table. So, suppose I want to know the cosine of 2/3 pi. If I want to know the cosine of 2/3 pi, I look at this first row until I find 2/3 pi, and then I read off the value of cosine. So the first entry, this first row, gives me the inputs, and the row below that gives me the output for cosine. If I want to know the value of an inverse cosine, I can use the table in reverse. So suppose I wanted to compute, let me give you a couple of examples. Let's look at cosine of 1/2 and cosine inverse of 1/2, and then cosine inverse of, how about minus √3 over 2. Okay, so those are two possible computations that you might make with the inverse cosine function. So the way that we can use a table to get those values is by saying, okay, I want to compute a cosine inverse. So the argument to cosine inverse is an output of the cosine function. So what I do is I look on the row with cosine to find that output value. And I see it right here. Cosine of √1 over 2, that's 1/2. So the input to cosine inverse is one of the output values of cosine. It's kind of a backwards way to think about it, but this way we don't have to learn a whole new table. So the output of cosine is 1/2. The corresponding input is pi over 3. So that tells us that the cosine inverse of 1/2 is pi over 3. Okay? Let's do one more just to get the idea. Again, if I want to find the cosine inverse of negative root 3 over 2, I find negative root 3 over 2 in the cosine line of our table. That's the output. And then I find the corresponding input. Okay? So the cosine inverse of negative root 3 over 2 is going to be 5 pi over 6. That's the basic idea about inverse cosine. Next, I'd like to show you inverse sine, show you how that's defined, show you a graph of it, and then do some quick computations to see how we can use the table. You'll find that it's the same kind of idea that we just followed to evaluate these cosine inverse expressions. Okay? Just like cosine, when we're trying to define an inverse function for sine, we have to restrict the domain so that sine is 1 to 1. Okay? We know that if we look at sine globally, if we allow the argument to be any angle whatsoever, sine is going to reuse values. Okay? So let's plot a quick graph of the sine function. So if I start to graph the sine function, it might look something like that, and then like that, and then those pictures will repeat. Okay, so just like before, what we want to do is we want to disallow sine to reuse any of its outputs. We're going to start from 0 and expand outward until we have the biggest interval that we can capture where sine doesn't reuse any outputs. Okay, so as we start in near 0, we're in good shape because we're using different outputs, different outputs, different outputs, and then all of a sudden when we reach this peak, if we go beyond that peak, we'll reuse our outputs. So that would prevent sine from being 1 to 1, and we can't have that if we're going to be able to invert it. So we're going to get rid of that portion of the curve. And then over here, as we get to the bottom of this trough here, again, we would reuse output values anytime we go beyond the minimum there. So we're going to disallow all of that. That leaves us with this portion of the curve, and it turns out that this is going to go from, this turns out to be negative 90 degrees, or negative pi over 2, and this is positive pi over 2. The output values for sine at those locations are positive 1 at pi over 2, and then down here we're at negative 1. Okay? If we want to draw a graph of the inverse sine, we know that we can do that by switching the roles of the inputs and the outputs. So we can flip this curve around the line y equals x, if we're thinking about x and y as our horizontal and vertical components, or y equals theta, if we're using theta for our horizontal component. If we flip that over, it turns out this is a little bit easier to draw. It ends up looking like that. Okay? And the domain of this function, just like before, varies from negative 1 to 1. This is the domain of the inverse function. And the outputs vary from negative pi by 2 to positive pi by 2. My scale on this picture is not that great. It's not quite to scale. But that's going to be what happens, is this curve flips over that diagonal line. And the plot of sine inverse looks something like this. We'll call it sine inverse of x. Right? So here we had sine was taking the input domain, negative pi over 2 to pi over 2, and it took it to the range of negative 1 to 1. So the sine inverse is going to take a domain of -1 to 1 into a range of -π/2 to π/2. We're swapping the roles of inputs and outputs. Okay? All right, now let's take a look at doing some computations with the inverse sine, or just evaluating the inverse sine. So let's look at inverse sine of 1/2, and how about inverse sine of -1? Okay, I've chosen two inputs that are within the domain of the inverse sine, and I expect to see outputs that vary somewhere between -π/2 and π/2. Okay. So if we want to evaluate the inverse sine of 1/2, we look for 1/2 as an output of the sine function, and we can see it right here, and the value of the inverse sine is going to be the argument or the angle that produces that output. So we look through our table, we see that this is the location where sine takes the value 1/2. So the inverse sine must give us the corresponding angle. That would be π/6. Okay. And then sine inverse of -1. We want to go through the table and find out where sine takes on the value -1. That looks like here, if we simplify it, square root of 4 is 2, 2 over 2 is 1. So this is an output of the sine function being -1. So the sine inverse of -1 must be the corresponding angle that produces that. So that has to be -π/2. Okay? So that gives you kind of a rough idea of the definitions of the inverse sine and the inverse cosine. In case you see them, there's another notation that's accepted for the inverse trig functions, and that's the use of the prefix arc. So if you see arc sine as a function, that's exactly the same as the inverse sine function. And then if you see the arc cosine, that's exactly the same as the inverse cosine function. It's just a different notation for that inverse function, and one that sometimes can actually be easier because it doesn't suggest or it doesn't allow you to get confused about this exponent. It's important, it's really important to understand that the inverse sine and the inverse cosine are not the same as secant and cosecant. These are not 1 over sine and 1 over cosine. We're using this exponent to stand for inverse function, not for a power, a standard integer power. Okay?